Assalamualaikum and a very good evening to the organizer and all the participants. I am Nur Asma and today I would like to present my paper entitled Modification of Photoanode Surface Structure via Image Analysis based on Organic Polymer Material for Dye-Sensitized Solar Cell Applications. Solar cell is a device that converts light energy directly into electrical energy by using photovoltaic effect. Solar cell can be divided into three generations, which is first generation, second generation and the third generations. First generation is crystalline silicon solar cell, second one is cadmium telluride solar cell, and the third one is dye-sensitized solar cell. In this study, we are focusing on the third generation solar cell, which is dye-sensitized solar cell. Why we choose the SSC as our project research is because it has simple and low cost of fabrication process, and it also lightweight and portable to be used. Nowadays, the SSC had been implemented in many applications such as lighting applications, flexible display panel, and small screen devices. To gain high efficiency in the SSC, there are several key techniques that need to be looked up, such as photoanode, our working electrode, dye sensitizer, counter electrode, and also electrolyte system. As I mentioned from the title of my study before, the part that will be highlighted in this study is the working electrode or photoanode. To have a good working electron in the SSC, the material structure need to have a few characteristics such as high surface area, high porosity, high stability, and high conductivity. Mechanism of the SSC started as the incident light or photon is absorbed by the dye sensitizer, and due to the photon absorption, the electron got promoted from the ground state to the excited state of the dye. Then the excited electron are injected into the conduction band of TiO2, which lies below the excited state of dye, where TiO2 absorbs the photon, and as a result, the dye gets oxidized. These injected electrons are transported between TiO2 and diffused toward the back contact of the ITO glass. Through the external circuit, the electron reached at the counter electrode. The electrode at counter electrode reduce iodide to triiodide, where the dye regeneration takes place and due to the acceptance of electron. Again, the oxidized mediator diffuses toward the counter electrode and reduces to iodide ion. On to introduction part. One of the main problems that the SSC have is the instability in the photoanode, or what we call as working electrode. And to enhance the performance of the SSC, this study will focus on the modification of TiO2 photoanode surface structure. TiO2, or what we call as titanium dioxide, is one of the material used in the photoanode surface due to its characteristics such as stability, and it has wide bandgap and environmental friendly, and due to it, it is non-toxicity. And this study also will focus on the effect of organic copolymer material that will be introduced in the photoanode surface structure. Even though TiO2 have good characteristics, TiO2 also has several disadvantages. The first one is TiO2 structure have poor dispersion and aggregate among themselves on the substrate. Okay, and as a solution, we are using the organic copolymer material in TiO2 photoanode in order to smooth the TiO2 surface structure. The second problem arises as the low efficiency of the SSC is due to the low dye absorption in the process. And to solve this problem, we are controlling the natural properties of TiO2 film, such as the porosity and particle size distribution of TiO2. The organic polymer material that will be used are from the polymer template type, which is also known as organized template. By introducing this polymer template type to TiO2, it will increase the transmittance of transparent substrate by improving the scattering layer in the SSC. And besides, it also will restructure the agglomeration of TiO2 particles to become more organized, which can enhance the electron lifetime. In this study, the example of the polymer template type is the poly-2-methoxy 5,2 ethihexyloxy 1,4 vinylene, which is MHPPV, and polystyrene sphere or PSV. In this study, there are two objectives that need to be achieved, which is the first one is to optimize the best weight ratio of MEH, PPV, and PS-sphere in TiO2 during photoanode fabrication in terms of surface roughness, porosity, and electrical conductivity of the SSC. The second one is to compare the efficiency performance between MH-TiO2, which is MH-PPV, and PS-TiO2, which is PS-sphere. For working electrode part, the first step is by preparing the stabilizer, which is the nitric acid and distilled water. Both of it will mix and stir 2 to 5 minutes. And then, before adding the stabilizer into the TiO2 paste, 1 ml of organic polymer, which is MHPPV and PS-sphere, was added into the TiO2 powder. And then, little by little of stabilizer was added until TiO2 paste were formed. And then, the TiO2 paste will be spread evenly on the surface of ITO glass by using Dr. Blade technique. The sample then were annealed for 1 hour for 450 degrees Celsius in the furnace. And then the samples were sent to the SEM image and the image T to check the porosity and particle size distribution. After that, the sample was soaked in the dye sensitizer, which is we use M34571 or ruthenium dye for 24 hours and were kept in the dark place. Tomorrow, the sample were taken out and cleaned by using acetone. And then for the counter electrode, we are using platinum paste, which is we use the same technique as for working electrode. We use doctor blade technique where we spread evenly on the ITO glass and we bake for 350 degrees Celsius for 30 minutes. And then the photoanode and the photocathode, or the counter electrode and the working electrode, will clip together and the electrolyte is dropped between it. And then both of it will clip and will send to the electrical conductivity of the SSC test. Result part. Okay, from the figure 1, the result showed that the same image of modified and unmodified TiO2 with MHPPV in different weight concentration. We differentiate the modified and unmodified TiO2 with the addition of modified TiO2 by adding the organic polymer into it. We call it as MHTiO2 and PSTiO2. And then for the unmodified TiO2, we just only call it as unmodified TiO2. From figure 1A is the unmodified TiO2 where no MHPPV was introduced, and we can see that the TiO2 particle on the surface are less compact and like crumpling to each other, but where the crumpled part is not aggregate smoothly on the surface of the ITO glass, where it can troubling or it can affect the performance efficiency of the SSC. And as the weight percentage of MHPPV in TiO2 increased, the TiO2 structure was becoming more better, where the porous structure will form due to the evaporated of MHPPV during the annealing process. We can see it in the result 2 showed the same image after being analyzed under image T program. As you can see from figure 2, the white area showed MHTiO2 and the black area showed the unfused space. The black area decreased as the weight concentration of MHPPV in TiO2 increased. From the table 1, the porosity of the MHTiO2 increased from 44.02% to 44.29%, but decreased to 42.51% for 1.00 weight concentration. The decreasing of 1.78% in the porosity of MHTiO2 in 1 weight percentage is probably due to the small interparticle distance between TiO2 and MHPPV. With the particle size increase, the number of holes for the TiO2 particle also increased. And then this is due to the dispersion of particle in the paste related with the degree of mixing TiO2 with MHPPV that gave impact on the pore size distribution. From the table, the unmodified TiO2 gave the efficiency with 0.00053%, where the device of MHTiO2 with weight concentration of 1% give the highest efficiency compared to TiO2 only. For PSTiO2, as you can see from the figure 3, it showed that the same image of PSTiO2 with different weight concentration, which is 0.25, 0.5 and 1%. So from figure 3B, it showed the surface TiO2 particle is less crumpled compared to figure 3.1a, which is the unmodified TiO2. As the weight concentration of PS sphere increased, it showed that the bigger pore structure started to appear more on the surface. You can see from table 2, the porosity of the photoanode increased as weight concentration of PS mixed in TiO2 increased, but decreased at the highest concentration, which is 1.00%. Larger pore will form as the weight concentration increased and help in increasing the porosity surface structure. The table showed the sample for PS TiO2 with highest efficiency of 0.08% of weight concentration 0.5% compared to the unmodified TiO2. For the summary, the fabrication of the SSC by using organic copolymer material was successfully fabricated. MHTiO2 with weight concentration of 1.00% and PSTiO2 with 0.50% had shown the highest efficiency compared to unmodified TiO2. The porosity and the particle size of TiO2 affect the performance of efficiency due to the dye absorption and the surface structure. MHTiO2 and PSTiO2 improve the surface structure of TiO2. That's all from me. Thank you.